All right, let's talk about graphs of equations. We're going to start with one variable. So we'll look at an example. Let's take x squared equals 4. So since there's one variable involved here, we're going to have a one-dimensional continuum. So this would be like the x-axis, but that's the only axis there is. So we know this as a number line. And the fundamental idea here of the graph of this equation would be that we want to plot in this number line all of the solutions to the equation. So this equation x squared equals 4 has two solutions. We've got x equals -2 and x equals +2, right? So the graph of that equation would be those solutions plotted in the one-dimensional continuum space. So somewhere in there we've got 0, let's see, 1, 2, 3, -1, -2, -3. So I would simply plot this point and this point. Okay, so that would be the graph of that equation in this one-dimensional continuum. You could also consider this equation with this restriction, but you consider that as like in a two-dimensional continuous space, and then you get, instead of 2 points, you would get 2 vertical lines. But anyway, that's just kind of an aside. Let's move on to two variables, which is what we're going to spend most of our time working with. For this one, I want to take the example 3x plus 2y equals 12. All right, again, the fundamental idea here is that we want to plot in our two-dimensional continuous space some solutions, right? We want to plot not some, but all the solutions to this equation. But what are those solutions? Well, I mean, you can just guess some values for x and y. Like, let's say we ask what happens when x equals 1 and y equals 4. I'm going to represent that as an ordered pair like we do in the plane. Well, if x is 1 and y is 4, we would have 3 times 1 plus 2 times 4. That would give us 3 plus 8. And does that equal 12? No, that's 11. So no, 1, 4 is not a solution. How about 2, 3? If x equals 2, 3 times 2 would be 6. Y equals 3, 2 times 3 would also be 6. 6 plus 6 is 12. Yes, that's correct. Right? So in my plot, let's put some points down here. 1, 2, 3, 4, 5, 6, 7. That'll do. So I can take the point 2, 3, 1, 2, and 1, 2, 3, and I can plot that point right there in my xy plane. But this approach is totally impractical because I can't just keep guessing and guessing until I find solutions. I mean, for one thing, it turns out there's infinitely many solutions to this equation. Infinitely many different xy combinations that will actually satisfy this. So there's a much better approach, and that would be to specify the value of one of the variables and then solve for the other value using algebra. And one of the simplest, some of the simplest points that you can find for the graph of an equation are the axis intercepts. Let's do axis intercepts. The reason they're simple is because axis intercepts always have 0 as one of the coordinates. So if we want to find an x-intercept, what we want is a point where the y-coordinate is 0. So it's going to be a point in that form, something comma 0, right? So we'll take our equation and just substitute in 0 for y. 3x plus 2 times 0 equals 12. 2 times 0 is 0. Adding 0 does nothing, right? Remember the identity law, right? So this will just become 3x equals 12. So divide both sides by 3, and x has to equal 4, right? So that means this coordinate, this x-coordinate, was 4 for that point. So we'll find 4 on our x-axis, 1, 2, 3, 4. These aren't labeled here, but this is steps of size 1, or steps of size 1, yeah, 2, 4, 6. And there we go, we plotted the point. For our y-intercept, we do similar, but we'll have the x-coordinate be 0, which is going to give us 3 times 0 plus 2y equals 12. So that's just 2y equals 12. So y equals 6. So 0, 6. Plot that point up here. So that's probably one of the easiest approaches to graphing an equation, is just to plot the x and y intercepts if you can. Now, this particular equation I know is a linear equation, so that knowledge tells me that the graph will be in the shape of a line. So there we go. So now I have the graph of this equation, and it is a straight line, and it has infinitely many points on it, and those points correspond exactly to the x and y values, that combinations that will solve this equation, right? That'll make it a true statement. Okay, so that's the fundamental idea of the graphs of equations. And so a graph is kind of a geometric thing, right? But I just want to point out that it is representing something algebraic, right? And we are using algebra, solving equations over here, very simple ones, in the process of creating it. So the graph of an equation kind of gives us this bridge between algebra and geometry. A way to sort of connect them together in producing something we call analytic geometry, which we'll talk about more as we go. So, okay, I just want to mention in 3 variables, if you have a linear equation like x plus 3y plus 2z equals 6 is an example of a linear equation with 3 variables in it, x, y, and z. The type of graph you get from that in the 3D space is going to be basically a like plane. I think I'm just going to grab another piece of paper here to draw it. Write that equation again up here. X plus 3y plus 2z equals 6. Let's say we want to find the intercepts for this, like the x-intercept. Just like we did with 2 dimensions, we would essentially say, let's let the other variables be 0, right? So instead of just having y be 0, we have to have z be 0 as well. If you think about this 3D space, if y and z are both 0, you're on the x-axis. So make y and z both 0, and we get x equals 6, which gives us the point 6, 0, 0. So 1, 2, 3, 4, 5, 6, and I'll plot a point there. For the y-intercept, what you do is have x and z both be 0. If x and z are 0, then now we're on the y-axis, and then we get 3y equals 6, so that would mean y equals 2. 0, 2, 0. So I'll plot 1, 2, plot a point there. And then lastly, for the z-intercept, we would have x and y be 0, so it would be like 2z equals 6, which gives us z would be 3. So 0, 0, 3. So 1, 2, 3. And you'll notice now we have 3 points. We can connect them with a triangle, but that's not a line, right? So the graph of this equation is not a line any longer. What it actually is it's like a plane, a flat plane, which is actually kind of, I'm going to do my best to draw it here. It's actually kind of slanted in, in this 2D space here. Sorry, 3D space. It's kind of slanted, and it is passing through our axes at these particular places. So you can almost picture it as kind of this tilted plane, right? That's kind of sitting like that, and it's cutting through the axes in these intercept points. But otherwise, it's then going off forever in all in all directions. Infinite two-dimensional plane. Yeah. So kind of looking back now, we have different numbers of equations with different numbers of variables, right? And in the case of a one-variable equation in a one-dimensional continuum, the graph would be some points, a point or some set of points, like in this case. In the two-variable case, the graph of the equation is going to be not necessarily a line. It could be some curve. The more general word would be like a curve of some kind. It could be more than one curve, actually. There's lots of different types of things you could have there. And then in the 3-variable case, as we saw here, this was a plane, but it could be some curved type thing, which you call a surface. So the or potentially more than one surface, which satisfies that equation. So that's kind of what you get from graphs of equations as you go up with more and more variables, introducing more variables. And it's kind of a neat thing here. If you have one variable, you get this 0-dimensional object, which is in a 1-dimensional space. The points are sort of 0-dimensional, but they're in 1-dimensional number line. The curve for an equation of 2 variables is like a 1-dimensional thing, right? The curve itself is a 1-dimensional object, but it's sitting in a 2-dimensional space. And for the 3-dimensional surface over here, that surface is a 2-dimensional thing, right? Even if it's curving around, it's still like a 2-dimensional object, but it's sitting in a 3-dimensional space. So yeah, there's the basic idea behind the graph of an equation. We're going to do some examples next.